Welcome back. Today we're going to talk about functions. Okay, so a function is a set of ordered pairs, and we're talking about it today because we've seen ordered pairs in the last lesson where we had solutions to two variable equations. So these ordered pairs, or these solutions, create what we call functions. So a function is a set of all these ordered pairs where each value in the domain is paired with exactly one value in the range. Okay, well, what is a domain and range? The x values are what we call the domain, and the y values are what we call the range. So each x value, right, because domain means x value, is paired with exactly one y value. So a picture of what's going on here is that there's like an element from the domain that's taken by a rule into the range. So let's say that you have like an element 3 and you have a rule of y is equal to 2x. So we take 3 and we double it to get an element 6 in the range. 3 would be in the domain, it would pass through the rule to get 6 in the range. Okay, the set of all x values is the domain, and the set of all y values is the range. All right, some functions only have ordered pairs that define them, all right? So some functions only have a few ordered pairs that define them, while others have many, infinite amount of ordered pairs. So sometimes with word problems, there's only some values that we can put in for x, or only some values that we're allowed to get back out for y. And so there are restrictions there. So there's only a few ordered pairs that will be for the functions that are, usually there's restrictions with word problems. For other ones that are just a rule, there's no restrictions, and so there's an infinite amount of solutions. That means there's an infinite amount of elements, or there's an infinite amount of ordered pairs in the set that describes the function. Okay, so there's different ways of looking at what a function, of seeing a function. So you can represent a function as a table, as ordered pairs. You can represent a function with tables and using mapping diagrams. So this is some of the things that, let me see if I can make this a little bit bigger. It's already pretty big, actually. Let's say that there's a fundraising program. It awards $30 for first place, $20 for second place, and $10 for third place, and $5 for fourth place. So this particular function, there's only 4 things that are defined here, 4 sets of ordered pairs, or 4 ordered pairs rather, that are defined for this function: 1, 30, 2, 20, 3, 10, and 4, 5. So notice that they're using, to define the function, they're using these curly brackets, which is set notation. These are the curly brackets right here. We saw them before when we talked about solutions to absolute value equations. So inside of the curly brackets are these ordered pairs. Okay, there's 4 elements to this function. There's 4 items that define the function, and so you see them all inside these curly brackets here. Okay, so express this function as a table, a graph, and a mapping diagram. First of all, this right here is a way to express it in terms of ordered pairs. So we said that that's one way to express a function. That's one way to describe it, is to use ordered pairs. Let me just use a highlighter actually to show you this. So here's one definition of a function. There is your ordered pairs. The next way to describe it is to put the values into the table with these column headings, okay? This right here is a way to do the same thing with ordered pairs, but I guess we don't need to highlight the entire thing, but I was gonna highlight it and show this, but it does say it on the side. So this is a way to take the ordered pairs out of ordered pairs and to actually just define them in terms of a table. Another way that you could do it is by using a graph here. So the graph just takes the ordered pairs and plots them. So this is a more geometric interpretation of a function. It just shows uses the x and y plane in order to show what's happening with this function. Okay. And another way to show it is to use a mapping diagram. Now with the mapping diagram, what you do is you start with a set, and usually, always, you start with the domain. Okay, it usually is on the left, but it doesn't have to be. So you take elements in their domain and you use arrows to indicate what happens to them after they pass through the rule. Okay, Our rule was just defined with the sentence, the initial sentence. So there wasn't like you didn't multiply the ranking by a certain amount to get the prize in dollars. It was just defined by whatever was in this first sentence here. Okay. But it's saying that the ranking of 1 goes to prize dollars of 30, the ranking of 2 goes to prize dollars of 20, 3 goes to 10, and 4 goes to 5, and so on. So write each X value in the region labeled ranking and each Y value in the region labeled prize. Use arrows to connect each X value with the corresponding Y value. That's how this is a mapping diagram of a function. So 4 different ways to describe what this function looks like. Remember, this is the situation where our function only has a few ordered pairs that define it. Other ones have an infinite amount of ordered pairs. Okay, and we'll get into what it looks like a little bit later on. Okay, so the ordered pairs were 1, 30, 2, 20, 3, 10, and 4, 5 here. What are the domain and range of the function? Well, the domain as just a set of numbers is going to be, and I can use a curly bracket here, okay, is going to be just the x coordinates, right? 1, 2, 3, and 4. So 1, 2, 3, 4. And the range is going to be just the y values. Whoops, that's just an E right there. So the range is just going to be these y values, 30, 20, 10, 5, and I'll indicate that. That's where that highlight's going, right? So just to see where each highlight is associated with. Okay, so this is going to be, and usually we write a set in order, so I'll start with 5. We write it in numerical order, in, let's see, ascending order. So ascending means you are going up. I always think of it in terms of stairs. So 5, 10, 20, and 30. Okay, so that's how you can identify the domain and range. Again, we have a nice function that's only defined for 4 coordinate pairs. When we have a function that's defined for infinitely many pairs, we're going to have to use sets of numbers to indicate the domain, like all real numbers or all integers. Okay, so this is a mapping diagram, and what I want you to do is I want you to describe the function. I want you to go from a mapping diagram to ordered pairs. Now, to do that, think about what each element in the domain goes to in terms of the range. So for us, that 4 is going to 5. So that corresponds to the ordered pair of 4, 5. Negative 2 corresponds to 1. 5 corresponds to 6, and 0 corresponds to 2. Okay. Now, we didn't need to have the arrows going straight across. In fact, I could rewrite this diagram so that the arrows were going all over the place. So let me show you. 4, negative 2, 5, and 0. Let's rearrange this to be 5, 2, 6, and 1. And then I could reorganize my map. 4 goes to 5. See, negative 2 goes to 1, so I draw an arrow that way. 5 goes to 6, that would be this way. And 0 goes to 2. Okay. What's important here is that the arrow starts at, it's actually a ray, right? A ray has one endpoint and one arrowhead, so it indicates that it goes infinitely in just one direction. So it starts in the domain, and it brings an element from the domain into the range. Okay, so that the direction of the arrow is absolutely important here. Okay, and lastly, we said that functions are there's a certain description of a function. Okay, there are some relationships between the domain and range that are not functions. All right. So some relations are not functions. To be a function, each element in the domain is paired with only one element in the range. All right. Now, this is akin to the relationship between rectangles and squares. So I used a Venn diagram to show this relationship. So remember, a square is a rectangle with all sides that are equal, right? So every square is a rectangle, but not every rectangle is a square. The same thing goes with relations and functions. Some functions are relations. Some relations all functions are relations, but not every relation is a function. All right. So we want one element in, each element in the domain is paired with only one element in the range. So let's look at what we have here. So the first one, this is 1, 2, 3 goes to R, S, and T. So 1 goes to R, 2 goes to S, and 3 goes to T. So each element here is paired with only one element in the range. This is a function. Okay. Now let's look at the next one. So 1 goes to R, 2 goes to R, and 3 goes to S. If I were to represent them as coordinate pairs, it would be 1R, 2R, and 3S. Okay, so there is a concern here that 1 and 2 are both being sent to R, but let's reread this again. Each element is sent to only one element. Each element in the domain is sent to only one element in the range. So 1 is sent to R, 2 is sent to R. That is actually okay. What is not okay is the next situation. So this right here is a function because 1 is only being sent to one element in the range. 2 is being sent to one element in the range. It's okay that 1 and 2 are going to the same element as long as 1 is not being sent to two different places. Okay, this is like saying if I have a student in my room and I want the student to go to two different teachers. I say, okay, at the very same time, I want you to go to the science teacher and the ELA teacher. Well, one student can't go to two different places at once. But if I had two students, like 1 and 2 here, and I send them to the same room, that would be totally fine. Okay, the next situation here shows 1 going to R. So if I show that 1 going to R, 2 goes to R, but 2 also goes to S. And finally 3 goes to T. Okay, this situation is not okay because I repeat, 2 is going to two different spots. It's going to R and going to S. Okay, so what it looks like is 2 in the domain has 2 arrows going from it to two different elements in the range. This right here is a relation, not a function. Okay, what it looks like with ordered pairs is that the first coordinate repeats itself. All right, and in this last one, we have 1 going to T and 3 going to T. We already said that that was okay. If the second element of the second coordinate repeats itself, that's okay. It's only when the first coordinate repeats itself. Now we do have a situation where there's an element in the domain not being sent to anything in the range, and that is also totally fine. I would not write 2 comma nothing here. That's not a part of my function. The only thing that this function right here is would include is 1 comma T and 3 comma T. So this right here is a function because each element in the domain is being sent to only one element in the range. Okay, and that's the end of the lesson for today. Tomorrow we're going to pick back up with functions and we're going to talk about function notation. And we're going to talk more about graphing functions with their solutions. All right.